Okay, welcome to Learning Target 2. This is actually 2 lessons, and I'm going to try to just walk through them relatively quickly together. So I'm just going to try to do these together. So first, lesson 2 is actually about calculating probabilities on an interval. And so we start by asking, like, a continuous variable has data points that have a mean that is higher than the middle value. What might the histogram look like? The point of this was really just in class was to get people to actually draw histograms, to think about what a histogram might look like, and then to think about what the data actually looks like. So if you're drawing this, you can draw it yourself, but like you're really looking at a histogram, which is just a bar graph. All the bars are touching each other. When there's one point maybe that's pulling up the data very, very high, or you can see a lot of the data may be lower, and then some of the data is pulling it high. So we call this a right skew distribution. The mean is pulled to the right. We're going to get to that in the stats unit, but I just really wanted to see if you could remember what drawing a histogram might look like. Okay, so the learning target, we're going to cover this in this video. I know how a frequency polygon can be used to estimate probabilities on a continuous data set. I understand how the interval size can affect the accuracy, and I can calculate the probability that a certain data point lies within a specific range. The big idea is the area, and this is what we're really going to get to, the area under a probability distribution curve for a given range tells us the probability that a certain value lies within that range. So today is going to be all about calculating area. So we saw this before, like Chris has the tire store. Was the relationship between the area of the rectangles, the probability of each. This word probability density, this is actually a key. This is a probability density histogram. This is 4 bars. This actually, the area is calculated, or the probabilities are calculated by calculating the area. So I could go from like 9 to 9.5 and just really calculate that area as length times width, or base times height. So the area just tells us the probability. Textbook talks about frequency table, so how many times something comes up, a frequency histogram, which is the orange here, and a frequency polygon, which is really just a sided figure. It connects the midpoints of the data. So that's what a frequency polygon looks like. What we want to focus on is a relative frequency. So we really care about probability, relative frequency histogram, and relative frequency polygon. So here we actually have like an interval size of 10. Probabilities are just calculated by dividing the frequency by the total, which is 40, and the probabilities will add up to 1. Okay. The area under this curve, this is a relative frequency graph. The area under this curve does not add up to 1. The area under this curve adds up to 10 because the interval size is 10. But notice that they are the exact same shape. This here polygon and this polygon are the exact same shape. So what's the difference? The only difference is the probability that a given value lies in the interval is based on the data. So like instead of frequency, we've got probability, and the shape is the exact same. But we are waiting for that idea of calculating the area under the curve, which can't be done here. But you don't need to. Like, you've already got the probabilities. We already know the probability that you lie in certain intervals. Okay. What was the probability density? Recall that we were able to calculate probability that a value lies in the interval by calculating the area of the rectangles. We did this with the tire shop. It can only be done if the areas add up to 1. So that's not always the case. So probability density areas do add up to 1. When the interval size is 10, that can't happen. So it's just if the probabilities add up to 100%, but the interval size is 10, that doesn't work. When the interval size is 1, it does happen. Relative frequency graph is the same as probability density. If you don't have relative frequencies, if you have the relative frequencies, you don't need a probability density though. That's the key. So you don't need to go area under the curve unless you want to get more accurate than an interval size of 10. So here's a question for you. I'd like you to take some time to do this. you're just actually calculating the probability. This is the probability density. So we're going to take the area under the curve between 0 and 3. So I'm going to take some time to do that. The method that a lot of people use is like just taking rectangles. Some people like calculate area of the triangle. We notice that that 3 is really just off the axis, so we have to estimate where that is. What the method we're going to use eventually is to actually calculate areas of rectangles. And we're going to see that in the next lesson, which I'm going to show you right now. Okay, so if we actually just calculate the area of rectangles, the area of those rectangles, they're gonna kind of overlap. Like there's going to be a little bit of a rectangle that's going to come out because this is a straight line coming down. But where we overcount area, we're actually going to undercount area as well. So that's going to be the method we're going to use to find the area. Some discussion questions. These are just really to think about. If the area is 10, what we could do is just divide all the probabilities by 10. And that's what we're actually going to see in the next one. How does a frequency polygon help you to estimate the mean might be? I'm not really so much interested in this right now. Probability density graph is 1 point much higher. So these are really just things to think about. How do you know if you can calculate a reflection question if they add up to 1? If the interval size is 1, how does a frequency polygon help you to estimate where the mean might be? Probability density graph. And so I just really want you to think about the data. How does knowing the probability density graph is uniform help to simplify the process? A uniform distribution is the easiest one to calculate. It's just a rectangle. And so that was Chris's tire store. It's very easy to calculate. So there's some examples here, and I just want you to practice using relative frequency here, not frequency. Okay. Moving into lesson 2. Shortening the interval. We want to try this question, the area under a polygon warm-up. So we're going to calculate the probability that a waist size is between 30 and 38. So I want to share with you how to do this. If you don't have the handout, if you don't have this page, if you don't print off this page. But this is what we're looking at here: probability density of waist size. And so we've got this this picture of a curve, and this is probability density. So we'll tell you the area under the curve. There's something that Windows has called the snipping tool. When you open it, it will. I've got this one open already. I'll just show you. It's a very handy tool for copying and pasting. So if we can just highlight anything, and we can paste it into a report. So if we say edit copy, here I'm actually just going to I pasted it into Paint, and so I could actually draw some rectangles on there. So I want to show you the rectangles that we drew. So the question asks us to find the area under the curve between 30, which is down there, to 38. And so the method to do that is just draw these rectangles. And so if we see the area between 30 and 32, this is a little estimate. This is a good estimate for the area of the probability. We just do length, which is 2 times the height, which is just about 8.8. And then so that number, and it's 8.8% times 2, so you got about 17.6% right there. And that's the probability that you're between 30 and 32. The problem is you are overestimating the probability. You can see this little part here. But don't forget, like, this is not an exact science anyway. So to like say, well, a better method would be to like cut it here and then find the area of the triangle or something, or find the area of this triangle and subtract it off. But it's not an exact science anyway. We need to do an estimate anyway. Notice the next rectangle, we actually don't calculate this triangle, and then we do calculate another extra triangle. So it's still not accurate because we've got 2 extra triangles and we're not counting another one. A little bit more accurate as you do more, like now you're counting an extra triangle, so you're counting 3 and then not 1. And then the next one, to get the probability between 30 and 38, we can add up the areas of all these rectangles. And again, there is some overlap, but then there's triangles that we're not counting as well. It's not perfect, but it is a lot easier than having to worry about areas of triangles. We're just really looking at the area of these 4 rectangles. And that's going to give us the probability we're between 30 and 38. And so you can go ahead and do that. It's just 2, and then you estimate the different sizes. Okay? You can do that yourself, or you can do that from this video. Now I want to look at the we'll just keep moving on in the presentation. But this is the idea here, is just to understand this method. Go back to the learning targets, the exact same thing we just talked about. The next part I want to lead you through an investigation. It's from page 333, but really what they're asking you to do is create a histogram of data. And they give you the interval size length 10. So they give you this one that I've drawn in Google Docs. I left the data there in the Excel sheet that's in this folder. Here's some directions to actually do this, but I'm just going to walk through it anyway. So they give you the histogram with an interval length of 10, and then we actually draw the frequency polygon. We need to set up the points, like the midpoints here. And then we had to use the frequency from the diagram from our histogram. So we don't actually have to count the number that are between each interval, like Google Spreadsheet does it for us. And here's some directions for how to create it. So I want to show you what the graphs look like. And so the point was in the textbook they asked you to do it for an interval size length 20 and an interval size of 5. And so what happens is, like with 10, we have a certain number of rectangles. We really only have for each midpoint. So 1, 2, 3, 4, 5 rectangles. For interval size 20, we only have 1, 2, 3 rectangles. Interval size of 5, we actually have 1, 2, 3, 4, 5, 6, 7, 8, 9. There should be one in here as well. So there's actually going to be 10 rectangles on an interval size 5. And so the question that they want to know is, which one would be more accurate? And because when we do more rectangles, you can go back to the to this guy as well. If we wanted to get more accurate to do the area under the curve, we could just break this up into more rectangles. And if we break this up into more rectangles, it gets more accurate. We just, like, the rectangles are more narrow, and we don't have as much like extra space that we're calculating, and so we do get a lot better. The problem with that is you can't always just narrow it down. So if we have a waist size of 2 inches as the interval, a waist size of 1 inch would be better. A waist size of a half an inch would even be better. A quarter of an inch would be better. We just have to make sure that, number one, we're collecting accurate data. So we measure people's waists to the nearest less than a quarter of an inch. And number two, we have a lot of data. Because if we make a whole bunch of intervals, we saw that here, we have to make sure people are lying in those intervals as well. But it does get to be more accurate with the rectangles. Okay? Just a little bit of a conclusion from that. So I just kind of want to wrap up. But a little bit, and remember we're doing 2 days in one. But just a conclusion from that. Like, I want you to think about, we've got these polygons, these polygon graphs. But if you actually think about a regular polygon, you can imagine like a triangle as a wheel. And so a triangle as a wheel is not very effective. But a square as a wheel is a little bit better, and a stop sign as a wheel, an octagon, is a lot rounder. It works well. A circle is what we want. If a stop sign has 8 sides, a triangle has 3. 8, like, the more sides, the better. And that's exactly what we want here as well with this data. The more sides we have, the more rectangles that we're calculating, the more sides we have to this polygon, the better. 3 is not very good. 5 is a little bit better. 10 is even better. If we can do better than that, then we can do better. Notice this light bulb data. It's just the life of the light bulb in days. And you can look at this data more closer in your file, but it's not there's not a lot of data here. Not a lot of light bulbs were surveyed. It looks like about 40 light bulbs were surveyed, and they didn't really calculate days more closer than just to the nearest day. So if they go to a decimal, half a day, we can get to be we can do a lot smaller interval sizes. We have a 5-day interval here, but if we did a 1-day interval and had a lot more data, then we can do a lot more intervals. Okay, and that's really the point of this, is really just to talk about what we need to do to be able to calculate probability. Sorry about that. What we need to do to be able to calculate probability is we need a lot of data. We need accurate data. So we can ask questions like, what is the probability that a can of Coke is between 354.9 and 355.1? If we have a lot of cans of Coke and they've been very accurately measured, we can answer questions like that. So we can get closer and closer to that idea that what's the probability a can of Coke is 355? Because with continuous variable, we know that that's 0. So we need to open up a little bit of an interval, but don't really lose the quality here in the question. You need a lot of data and precise measurements to take advantage of small intervals. You can't do small intervals if you don't have a lot of data and it's not very precise. It may not be possible. It just costs a lot of money. It takes a lot of time. It takes a lot of time to collect data. It costs a lot of money to get precision. Some discussion questions. Probability calculated by finding the area under the curve is easy to calculate. What do you know about the data? Well, it can be uniform. If it's uniform, the interval sizes can be big because we're just really basically looking at a few rectangles. The probability that a data point is given inside an interval is very small. What can you tell me about the interval? The interval can be really small. Remember that to get probability, you need to calculate the area of the rectangle in that interval. And if that interval has a small base, that rectangle is going to have a small area. How can we ensure probability calculation is extremely accurate? Do a lot of measurements and do them very precisely so that we can have small intervals. We're going to see this. This is all going to culminate into the normal distribution, which comes up the next lesson. Okay, so here's some practice questions. I know that was pretty quick, but that kind of gets us through 2 lessons. And it's a good summary of where we're going to next.